Hello everyone, welcome back to Ronnie Explains. So this video we are going to look at the logic gates, which are basically one of the fundamental elements in the digital logic design. And we begin by looking at the OR gate. So the OR gate is a gate that shows true values, or rather a value of 1 when at least one of its input is true. It means when at least one of its input is 1. So this is what it means. It means that if we have values here like 0 and 0, all of them are false, and because of that the result becomes false. Here at least 1 is true, so 1 is true here, and that's why here we have a true value. Here 1 is true, that's why we are going to have a true value here, and all of them are true here, and that's why here we also have a true value. So OR gate is represented by a symbol that looks like this. If we want to write the logic expression of this truth table here, then we are going to write it as y is equals to a or b. And please note that this symbol here is basically a logic symbol for OR gate operation. It is not an addition symbol. Symbol that is used during the circuit design is a symbol that looks like this. So we have a curved part of the gate like this, and then this other side looks like this, and this side we have the input signals coming in as A, B, and then the output being given out as Y. So basically this is what an OR gate is. Then let's move to the next, which is an AND gate. An AND gate shows true values when all the input values are true. For example, here all of them are false like this, so therefore the value of y is also going to be false. But here one of them is true, therefore here is false, because all of them need to be true. The same case here, this is the same case as this, so because of that here is also false. But finally here all of them are true, and that's why here we have a value of 1. AND gate is represented by a dot, a symbol that looks like this, and sometimes we can just write the inputs continuously as AB, and that still means it's an AND gate. So the expression can be written as y is equals to A and B, or you can also write it as y is equals to AB. So all of them, they represent an AND gate. And the symbol that is used in circuit design for an AND gate is a symbol that looks like this. We have this like this, and unlike the OR gate, for an AND gate, this one is a straight line. For an OR gate, we saw that it was a curve. Then we have the input signals coming in as A, B, and then the output signal coming out as Y. And basically, this Y is equals to AB or A dot B. That's how we represent it. Then we move to the next gate, which is simply a NOT gate. A NOT gate is a gate that negates the input signals and give the result as output. So basically this is what it means. It means if the incoming signal is a true value as 1, it will be negated to give 0. If it is 0, then it will be negated to give 1. So if it is a value, for example, like A, then it will be negated to give A prime. If it is B, then it will be negated to give B prime. You can say that A is negated to give A bar, or B is negated to give B bar. So A bar or B bar is simply the same as A prime or B prime. Then the symbol for a NOT gate looks like this. We have this symbol like this, and over here we have something like a circle, and then we have the output going in out like that, and then the input as this. So if this is A, then this other side becomes A prime or A bar using. Then we move to the next, which is an OR gate. An OR gate is simply a combination of OR gate and NOT gate. So in short, NOT gate plus OR gate will give you an OR gate. So it means that we first have to check the OR gate for this. So the OR gate will be gotten by taking A or B, and A or B here, this becomes 0, this is 1, this is 1, and this is 1. Then we negate this to give us the value of Y. So the value of Y is basically A or B, but everything negated. It means this here now is the NOT gate. Now, in its implementation, we just have to negate all these values that we have here, and that's why this one becomes 1, this becomes 0, this becomes 0, and this becomes 0. So the symbol for a NOR gate looks like this. We will have almost the same sign as the one that we had for an OR gate, like this, but at the end of it here, we'll have something like a circle, and then we have the output signal and the input signals as A, B, and the output signal as Y. And this Y is equal to A or B, everything negated. That's how it works. Then we move to the next one, which is a NAND gate. A NAND gate is simply a combination of a NOT gate and an AND gate. So if you have a NOT gate plus AND gate, then this gives you a NAND gate. So basically this is how it works. We begin by looking at A and B, which can be written as AB, and then we check 0 and 0 is simply 0. Then this is also 0, this is 0, and 1 is basically 1. Then we negate the values this other side to get the value of Y, which is basically A, B, but everything negated like that. So here, this will be 1. After negation, 0 becomes 1, then 0 becomes 1, then 0 becomes 1, and 1 becomes 0. So this column here will represent the NAND gate. Then the symbol that is used in circuit design for a NAND gate is basically we take the symbol of an AND gate like this, and we add a circle here, and then we give it its output signal, and then we have the input signals as A and B. Then this other side we have the output as Y, and this will represent that symbol. So the logic expression for this becomes Y is equals to A, B, then everything negated. Then we look at the exclusive OR gate or the XOR gate. An XOR gate is a gate that gives a true output 1 when the inputs are different. So we have to check for different inputs, then we give a true output. So here we have an output as Y. Here the inputs are the same, and because of that this is 0. Here the inputs are different, and because of that the output is 1. Here they are different, and that is also 1. And here they are the same, and it means there now becomes 0. So this part here now represents the XOR gate. XOR gate, the logic expression for an XOR gate looks like this. So we can say Y is equals to A XOR B. But please note that this can also be represented as y is equals to AB prime or A prime B. And the symbol for an XOR gate looks like this. You will have the symbol for an OR gate like this, but this side you will have an additional curve here that looks like this, and then you have the input signals as A and as AB, A, X, or B. So that is how XOR gate looks like. Then we go to XNOR gate. An XNOR gate is a gate that gives a true value if all its inputs are the same. It means that if here we have Y, then we have to check if all the inputs are the same. So here they are the same, all of them, and that's why here is 1. Here they are different, and that's why here we have 0. Here they are different, and that's why we have 0 also. And here they are the same, and because of that we have here as 1. So therefore, this part here will represent the XNOR gate. An XNOR gate is simply represented by the same symbol as XOR gate, only that we put a negation sign, a bar or an hyphen, depending on the symbol that you're using. So this symbol that is used in circuit design is almost similar to the XOR gate, but it looks like this. So we have the curve like this, and again here we have this curve like this, but over here it has a circle, meaning it's negated. Then here we have the input values as A, and we also have B. Then the output is Y, and this Y is simply equals to A, X, or B, like this, but everything now becomes negated. Please note that Y is equals to A, X, or B can also be written as Y is equals to AB or A prime B prime. So that is how we implement the XNOR gate. So that's it from this video. If you enjoyed watching this video, please give it a thumbs up and consider subscribing for more upcoming contents. Thank you.